Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is week 3, part 2. In this video, we build on the core ideas of CNNs and examine their architectural components and early successful models. So here's our game plan. First, we're going to see exactly why we need convolutions in the first place by looking at why standard multilayer perceptrons just don't work for images. Then we'll assemble our architectural toolkit, the essential building blocks for any CNN. After that, we'll see how stacking these blocks together lets the network build up a powerful feature hierarchy. And finally, we'll put it all together by looking at a pioneering case study, the LeNet architecture. Okay, let's dive right in. To really appreciate just how clever the design of a CNN is, we first have to understand what goes wrong if we try to use the tools we already know. So why can't we just take a multi-layer perceptron and throw it at an image? Well, there are two massive problems. The first one is a parameter explosion. Think about it. Even a modest 1,000 by 1,000 pixel image has 1,000,000 pixels. If you connect that to a hidden layer with just 1,000 neurons, you're already at 1,000,000,000 parameters. That's computationally insane, and it's a recipe for massive overfitting. But the second problem is even more fundamental. You destroy the spatial structure of the image. By flattening that 2D grid of pixels into one long vector, you throw away all information about which pixels are next to each other. The network has no idea that 2 adjacent pixels are more related than 2 pixels on opposite corners of the image. The solution to both of these problems is the convolution operation. Instead of a giant, fully connected weight matrix, we use a small, learnable filter that we call a kernel. This little kernel slides across the input image, patch by patch. At each step, it computes a dot product between its own weights and the input patch it's looking at. We add a single bias term, and that gives us one number in our output grid. This elegant little mechanism solves our problems with two powerful principles. First, sparse connectivity. Each output neuron is only connected to a small local patch of the input. And second, parameter sharing. We use the exact same kernel, the same set of weights, across the entire image. So what does this output grid, this Z, actually tell us? We call it a feature map, and it's basically a map that shows us where the filter's preferred feature appears in the image. For example, look at this filter here. It has positive values on the left and negative values on the right. When you slide this across a vertical edge, a jump from light to dark, boom, it produces a really strong activation. It's literally a vertical edge detector. Now, the real magic of deep learning is that we don't have to sit here designing these little feature detectors by hand. The network learns the perfect set of filters for the task, all on its own, through backpropagation. Okay, so this core convolution operation is our star player. But to build a really deep and effective network, we're going to need a few more gadgets in our toolkit. These are all about controlling the shape, the size, and the scale of our feature maps as they move through the network. One side effect of convolution is that the output is always a little bit smaller than the input. If you have a really deep network with many layers, your feature map would just shrink away to nothing. Plus, the pixels around the border don't get as much attention from the kernel. The fix is wonderfully simple. We just add a border of zeros around the input. This is called zero padding. It does two things for us. It lets us control the output size, and it makes sure the pixels at the edges get their fair share of attention. And as you can see from the equation, we can even calculate the perfect amount of padding to make the output dimensions exactly the same as the input. Our next tool for controlling geometry is the stride. Stride is just the step size of our sliding kernel. A stride of 1, which is the default, means we move 1 pixel at a time, getting a very dense output. But if we use a stride of, say, 2, we skip a pixel with each step. This has the effect of downsampling, making our output feature map smaller. It's a great way to reduce the amount of computation and memory we need in later layers. Of course, there's a trade-off. You might lose some of the fine-grained detail in the process. So far, we've only been talking about 2D inputs. But a real color image isn't flat. It's a volume with a depth of 3 for the red, green, and blue channels. This means our filters can't be flat either. They also have to be 3D volumes. And here's the rule. The depth of the filter must always match the depth of the input. The convolution operation then sums across all 3 dimensions to produce a single value. So one 3D filter sliding over a 3D input gives you one 2D feature map. How do we create depth in the output then? Simple. We just use a whole stack of different filters on the same input. Each filter learns to find a different pattern, and we stack their 2D results together to form a new deep output volume. Another very common way to downsample is with a pooling layer. Now, unlike a convolution layer, pooling layers have no learnable parameters at all. They're just a fixed operation. The most popular kind is max pooling. All it does is look at a small window of values, say 2 by 2, and it outputs only the single largest value from that window. This is useful for two big reasons. First, it obviously reduces the size of our feature maps, making the network faster and more efficient. And second, it gives us a little bit of what we call translation invariance. If the feature that created that max value, that H you see there, were to shift around a tiny bit inside that window, the output wouldn't change. This makes our network more robust to small changes in the feature's position. Okay, we now have our complete toolkit: convolution, padding, stride, and pooling. We have our Lego bricks. Now for the really profound part. What is the magic that happens when we start stacking these layers one on top of the other? How does a deep CNN actually learn to see? To really get this, we need one key concept: the receptive field. It sounds technical, but the idea is simple. For any single neuron, anywhere in the network, its receptive field is just the specific region of the original input image that it can actually see, the patch of pixels that influences its final value. And this is where it all comes together beautifully. In the very first layer, the neurons have tiny receptive fields. They can only see little patches of pixels, so they learn to recognize very simple things: horizontal edges, vertical edges, little patches of color. But now, think about a neuron in the second layer. It's looking at the feature maps from the first layer, so its receptive field relative to the original image is bigger. It can see combinations of those simple edges and learn to detect more complex things, like corners or textures. As we go deeper, the receptive fields get larger and larger. Neurons in the middle layers can combine textures and shapes into object parts: an eye, a nose, a car wheel. And by the time we get to the final layers, the neurons have such a large view of the input that they can piece all these parts together to recognize high-level concepts, like a whole face or an entire car. It's this incredible hierarchy of features. And the amazing thing is we build this powerful structure out of a simple, repeatable block. The typical CNN architecture is just a sequence of these stages. Each stage usually has a convolution layer to find features, a nonlinear activation, like ReLU, and then often a pooling layer to downsample. You just stack these blocks: conv, ReLU, pool, conv, ReLU, pool, over and over. This whole stack of blocks acts as a deep feature extractor. Its one job is to transform raw pixels into a rich, high-level representation. Then, at the very end, we flatten that final feature volume into a vector and feed it into a standard dense classifier, an MLP, which we call the head. So the convolutional base does all the hard work of perception, and the head just makes the final.
All right, that's enough theory. Let's ground all of this in a concrete historical example. We're going to look at one of the very first successful CNNs, LeNet 5, which brought all these ideas together.
This was developed way back in 1998 by Jan LeCun and his team, and it was designed to read handwritten digits, like you'd find on a check. The architecture should look really familiar to you now. You can see the pattern: a convolution layer, C1, followed by a pooling layer, S2. They called it subsampling back then. Then the pattern repeats. After that, the features are flattened and passed to a couple of fully connected layers for the final classification. Now, it used average pooling instead of max pooling and older activation functions, but the fundamental blueprint is all there. And this was a huge deal. It was the first really compelling proof that you could train a network with this kind of hierarchical structure from end to end to solve a practical computer vision problem. So this raises a big question. If LeNet showed how powerful this was back in 1998, why did we have to wait until 2012 for the deep learning revolution to really take off? Well, for over a decade, progress was stalled by a perfect storm of three big problems. First, there just wasn't enough large-scale labeled data to train bigger models. Second, CPUs were simply too slow to handle deep networks on larger images. And third, a nasty technical issue called the vanishing gradient problem made it incredibly difficult to train very deep networks. The breakthrough in 2012 happened because we finally solved all three problems at once. We got powerful GPUs for massive parallel computation, huge datasets like ImageNet became available, and new algorithms like the ReLU activation function helped fix the gradient issue. So, to quickly summarize our key takeaways. First, the core of CNNs is learning local features using kernels with shared weights. It's both powerful and efficient. Second, we have our toolkit of padding, stride, and pooling, which gives us fine-grained control over our network's architecture. Third, and this is the big one, stacking these layers lets the network build a powerful feature hierarchy, learning to see complex objects from simple patterns. And finally, LeNet 5 was the foundational proof of concept that put all these ideas together and showed the world that this approach really worked. And that brings us to our final question to think about. The principles behind LeNet were proven on small, grayscale images of digits. So how did we scale these exact same principles up to conquer the incredible complexity of high-resolution, real-world images? That is the story we'll tackle in our next video, as we explore the advanced architectures like AlexNet, VGG, and ResNet that truly sparked the modern deep learning revolution. Thank you.